Welcome to This Explainer. Let's just jump right in. Today, we're diving into something you probably interact with dozens, maybe hundreds of times a day, but I'm guessing you rarely think about it until, it stops working. We're talking about the electrical grid. But here's the thing, this isn't just a boring network of wires and poles. It is an incredibly intricate, deeply fragile machine that is basically attempting the most dangerous zero-inventory high-wire act in modern history. The grid doesn't work like a normal supply chain at all, and right now, it is being pushed to its absolute breaking point by a massive, sudden surge in demand. So let's unpack exactly why the grid is currently in a desperate race against time. To really wrap your head around just how fragile the grid is, you first have to understand this one specific number, 60 hertz. Unlike oil sitting in a massive tank or, say, grain stored in a silo, electricity is the only major commodity on Earth that has to be manufactured the exact instant it's consumed. I mean, the entire US grid has essentially zero inventory. The storage we do have is measured in mere minutes of national consumption. The whole system acts as this one giant, interconnected machine that is constantly, second by second, balancing supply and demand. And 60 hertz? That's the real-time inventory gauge. So when you flip a light switch in your kitchen, a power plant somewhere has to spin just a tiny fraction harder to maintain that perfect 60 hertz frequency. It's wild to think about. All right, Section 1. The zero inventory tightrope. Dominoes at light speed. So because the grid is spinning in this perfect 60 hertz synchronization, losing that balance isn't just an inconvenience, it's physically dangerous. If demand spikes suddenly and the turbines start to slow down, the frequency sags. And if it drops too low, the massive steel blades inside those power plants will literally start to destroy themselves from resonant vibration. So what do? They automatically trip offline to protect themselves. But when one generator or even one power line trips, well, that electricity doesn't just vanish into thin air. It instantly reroutes to neighboring lines at the speed of light. And guess what? Those neighbors suddenly overload and they trip too. It's a cascading blackout spreading like light-speed dominoes. This is exactly what happened during the massive 2003 Northeast blackout. An untrimmed tree branch in Ohio shorted out one single power line, and within an hour, boom, 50 million people went completely dark. Moving on to Section 2, an aging, bottlenecked skeleton built for your grandparents' economy. Let's look at the physical hardware doing this zero-inventory tightrope walk because, well, it is remarkably old. Most of it was built for the post-war boom back in the 1960s and 70s. Roughly 70% of our transmission lines and power transformers are operating way past their original 40 to 50-year design life. We are essentially trying to run a high-tech 21st century economy on a totally aging delivery skeleton. And the ultimate choke point of this whole aging system? It's the large power transformer. These things are massive. They are custom-engineered machines the size of a small house, weighing up to 400 tons. They handle hundreds of megawatts, stepping the voltage way up so it can travel long distances, and then back down so you can actually use it in your house. But here is the really terrifying part. Almost no two are identical. They are entirely bespoke. And because every transformer is basically a custom job, you can't just keep generic spares sitting on a shelf at Home Depot. If a utility wanted to order a large power transformer before 2020, it would take a few months. But now, that wait time has blown out to 2 to 4 years. Some quotes are even hitting the 5-year mark. On top of that, prices have skyrocketed by 60 to 80%. And considering the US currently imports about 80% of its large transformers, well, every time an aging piece of equipment fails and the replacement is going to take 3 years to show up, it exposes the grid to this incredible, totally unhedged risk.
Now, you might be thinking, okay, why not just build more transformer factories, right? Well, the deepest choke point actually isn't the factory assembly line. It's the raw materials, specifically something called grain-oriented electrical steel, or GOES. This is a highly specialized magnetic steel that you absolutely need for the core of the transformer, and it is genuinely incredibly difficult to manufacture. The US relies on essentially one single domestic producer for the stuff. Building a brand new facility to produce this specialized steel, that's a structural bottleneck that takes 4 to 5 years and well over $1 billion to fix. And so far, nobody is really committed to doing that at the scale we need.
Okay, Section 3, the AI demand sprint, waking up from a 20-year nap.
So, against this crazy backdrop of an aging, bottlenecked grid, we suddenly hit a massive wall of new demand. For about 20 decades, US electricity demand was, well, basically flat. Utilities got totally used to the zero-growth environment.
But all of a sudden, we are waking up from a 20-year nap and facing a massive demand shock. And roughly half of that growth is being driven by AI data centers. What we have here is a high-stakes race between a tech sprinter and a grid tortoise. Think about it. A massive, brand-new AI data center can be built and ready to suck up power in just 1 to 2 years. But building the firm grid power, upgrading the transmission lines, and waiting for those bespoke transformers to arrive, that takes 5 to 10 years. We are trying to plug the absolute most power-hungry technology in human history into a grid that moves at the sluggish speed of heavy industry.
Which brings us to Section 4, the interconnection traffic jam, a bouncer at the grid's front door. Think of the grid's interconnection queue like a really strict bouncer outside an exclusive club. Before any new power plant can plug in and start selling electricity, whether that's solar, wind, or natural gas, it has to be extensively studied to make absolutely sure it won't overload those aging wires and transformers we just talked about. Right now, the line outside that club is unimaginably long. Just to put it in perspective, the entire existing U.S. power fleet, every single nuclear plant, coal plant, gas plant, and solar farm operating today, adds up to about 1,300 gigawatts of capacity. But waiting in the queue right this second, over 2,600 gigawatts of proposed new power. We literally have twice the size of the entire existing U.S. grid just standing in line, waiting for permission to plug in. But here is the stark reality of that massive 2,600 gigawatt number. Most of it is a total mirage. Historically, only about 13% of the projects that enter that queue ever actually make it through the process and get built. Why? Well, because it costs almost nothing to submit an application, so developers submit multiple, highly speculative projects, which completely clogs up the study process for everyone else. By the time a real project finally gets approved years later, the required grid upgrade costs assigned to them are often so insanely high that developers just throw up their hands, cancel the project, and walk away. Section 5. Why noon isn't winter. The reality of free energy. With all this crazy new demand and grid congestion, you might be sitting there thinking, wait, haven't I seen headlines about solar power becoming incredibly cheap? And you have. Thanks to Wright's Law, which basically states that costs drop by about 20% every time global production doubles, the cost of solar panels has absolutely plummeted. I mean, they are dirt cheap now. So why isn't our electricity completely free? Well, in some places, midday solar energy is so abundant that wholesale prices literally drop below zero. But we have to remember the physical limits of the universe, right? The sun eventually sets, and that dirt-cheap solar panel still requires a multi-million-dollar transformer that takes 3 years to arrive just to physically connect to the grid. So free noon energy in June is absolutely not the same thing as free electricity at 7 p.m. in the dead of January. Actually, this whole transition to clean energy is the most transformer-intensive event in the entire history of the grid. We are generating tons of incredibly cheap electrons in the middle of the day, for sure, but we are desperately bottlenecked by the expensive, hard-to-source physical machines required to deliver those electrons when we actually need them the most, like on a freezing, dark winter evening. Now, to bridge that gap between noon and night, grid-scale lithium-ion batteries are absolutely booming right now, especially in places like Texas and California. These 4-hour batteries are brilliant. They are perfect for capturing that cheap midday solar and discharging it to flatten out the daily evening demand peak when everyone gets home from work and turns on their AC. But while they totally solve that evening problem, batteries run out of juice pretty fast. They simply cannot provide power for 48 or 72 hours straight during a massive multi-day winter freeze when the sun isn't shining. To survive a massive multi-day winter storm, you desperately need what the industry calls firm backup power. These are generators you can just turn on and run continuously for days, like natural gas, nuclear, or hydro. But here's the kicker. If a utility wants to build a new natural gas plant today to provide that firm backup, they'll smash right into another massive supply chain wall. The heavy-duty gas turbines required for these plants, they are completely sold out by manufacturers until roughly 2030. No joke, you literally cannot buy one right now for near-term delivery. Time to power has officially become the most valuable asset in the entire energy market. Which brings us to our final section, the final sprint, reaching the destination. So, to recap, we have a zero inventory grid balanced on a knife's edge, an aging skeletal system, and a tech sprinter demanding ridiculous amounts of power today from a tortoise-paced supply chain. There is a quote from our source material that I absolutely love because it just hits the nail on the head. It says, "The destination of cheap, abundant energy is plausible. The transformer shortage describes the road."
A future powered by incredibly cheap solar, huge batteries, and AI is entirely possible, and we are definitely moving toward it. But the road to get there, it is not paved with software. It's a massive, physical infrastructure traffic jam, gated by bespoke magnetic steel cores, 50-year-old transmission wires, and gas turbines that are sold out for the rest of the decade.
The tech industry is sprinting forward, practically demanding massive amounts of electricity right now to power the future. But the physical grid, our tortoise, is bound by the hard laws of physics, 40-year-old hardware, and a seriously choked supply chain. So as the gap between that sprinter and the tortoise continues to widen over the next 5 to 10 years, how exactly will our fragile zero-inventory grid survive this massive traffic jam without stumbling into the dark? It is, without a doubt, the most important race of our time, and the clock is definitely ticking. Thanks so much for joining me on this explainer, and I really hope this gives you a whole new appreciation for what's actually happening behind the wall the next time you flip a light switch.